Okay. I'm hoping that my audio is working. I can see it. Anyways, so if you're trying to do chain rule, there's two main ways you can go about it. Um, Let me just change my color. Okay, so there's two main ways you can go about it. There's the one where you use function notation, where if you have, let's say, fx. Actually, I don't like this color. This one's just black. Okay, let's just say you have something written in function just functionally. So if you have fx equals to g and then with another function embedded in it, then the derivative, you would differentiate the outside function first. So g dash h of x, where you don't touch the inside function at all, and then you multiply this by the derivative of x. And this could actually go on just indefinitely, because if this function here, the hx, had something inside it as well, you can kind of just keep continuing the progression, right? So another example, I'll use different variables. So let's say I have a, b, c of x. So function c is inside function b, which is inside function a. I don't know how many brackets I'm gonna need. So I'll differentiate function a first, and then I don't touch anything on the inside. Okay, I just realized C kind of looks like a bracket, but yeah, just ignore that. So I've done that. Uh, Let me just okay. I'll start from explaining this again. We're differentiating the most outside function, which is the a, hence why I have the a dash right now. And then what follows here is the derivative of everything that's inside. So this thing. Now, if you're looking at the derivative of this entire thing, you'd have to use chain rule again, right? And the first step of differentiating something like this is to first differentiate the outside once again. Uh, and then it kind of just repeats, right? So yeah, it can go on for a while. That's one way you can kind of think about doing chain rule, which is, I believe, what you're doing. There is another way, and that's basically using the dy dx notation. So we know how dy dx is equal to dy du times du dx, where u is generally something that's inside your equation, or like the inner function. So usually this thing would be the u. Okay. Um, what's a quick example? Let's just say like I have y is equal to 2x plus 3 to the power of 5. So with the left hand side, I guess I could write it as fx equals to 2x plus 3 to the power of 5. Um, and then on the right hand side, I'll just keep it like this. Actually, I'll define u as the inside function. U equals to 2x. No, actually, no. I'm going to do them one at a time so you don't get confused. So over here, um, and I know one of your questions is how do I determine what's the inside function, what's the outside function? So just bear with me. I'll get to that later. And okay, what was I doing? Chain rule, right? So the derivative of this is I would recognize the something to the power of 5 as just the standard power rule, and I'll deal with that first. So 5 of something to the power of 4. That's the derivative of the outside. I don't really care about what's on the inside because I'm not going to touch it anyways at this stage, at least. Um, so yeah, it's not too important, but this is the general structure. And then you can just fill out whatever's on the inside, right? Because that's honestly not too important. And then you're differentiating whatever's on the inside. So it's a 2. Yeah, so simplifying everything. Actually, I'll just leave it like this. But, obviously, if you're on a test, simplify. Now, the other way to do this is to kind of define what's on the inside. So 2x plus 3. And then this would make y is equal to u to the power of 5. Now, why would you do this? The reason why you would split this into two equations is so that, well, you can't, maybe you find it hard to differentiate something that's complicated. So you would split it into multiple equations in which you know how to differentiate, and then we combine them together. So yeah, that's your goal of subbing a u in there. It's to make the differentiation step easier. It's for you to be able to utilize some formulas that you know, right? So if you're making the wrong substitutions and you're looking at your two equations and you're like, oh, this is not much better, well then you're doing something wrong, right? I'll give you a wrong example. So for instance, let's say you said u was purely just the 2x on the inside. That would be wrong. Like that's very wrong. So your y would be what? Like u plus 3 to the power of 5? Okay, it's like I can differentiate this, but this is still a bit of a question mark, right? I still have to utilize some sort of chain rule, which I'm gonna assume we don't have here because that's all we're trying to learn right now. Um, so yeah, you're gonna be stuck with some issue like that. So make sure you pick your u wisely, such that the equations actually do become easier. So now it's just a matter of doing both of them separately. So 4u5, and this is my handwriting is a bit crooked. Du dx is equal to 2. So let's just quickly observe both of these things. Now, this part looks very, very similar to this part, right? Where if I ignored this thing, they kind of have a very similar structure, where the u represents the inside function, and then the 2 at the back is just the 2 at the back, the derivative of the inside function. And then again, just following the formula that I've stated up here, you multiply them together to get obviously the same answer as this. So yeah, two ways of thinking about it. I know you're doing it from the left perspective, in which it kind of relies on you to um, figure out what's the inside function. Um, the right method, I guess it's more algebraic in the sense that as long as you don't make any mathematical errors, you don't have to like try super hard to figure out what's inside and what's outside. Because like I said, if like, okay, obviously this is the inside function and you have to still define that yourself, right? But the advantage of this over this thing is that if you get this wrong, you just can't do the question, so you know something's wrong, right? Um, yeah, but if you pick the correct inner function, then the question will work out for you. So in that sense, this is, I guess, more algebraic. Um, but if you're but this is longer because you have to set up two equations and then differentiate them separately and multiply them together. Whereas for the left method, it's faster, but you have to do more things in your head, basically. So, how do you know whether something is the inside function or not? Let me just chuck this down here. So I'll just list down some of the formulas that we would have looked at. So just just something general, right? d dx, x to the power of n is equal to n x n minus 1. D dx, I mean, what else did you send me? Oh, tan ex. Okay, d dx tan x is equal to what? Sec squared x. D dx e to the power of x is equal to e to the power of x. And I'm using the most basic formulas there are for good reason, because we gotta take into consideration what everything's being differentiated against, and we're differentiating everything with respect to x, right? As we can see in the variable down here. Um, and I'm gonna try to color code that. I'm gonna change all the x's to a different color. Uh, so like x to the power of n. Okay, so you can kind of think of the x as um like a location for an inner function to exist. So, or instead of writing x, I could just replace this as a box, right? So if anything follows this form, then that could be the inner function, like whatever goes inside. You can use this formula as the outside function, where whatever's on the inside is the inner function. For instance, if I have d dx of 2x plus 3 to the power of 5, if you kind of just ignore whatever's on the inside, this takes the form of a power rule formula, right? And of course, you have to multiply by the derivative later on, as the chain rule states. And let's take a look at the second case, which is I think what you mentioned. Um, so I think it's this one, right? 10. I don't know. I'm hoping it's this one. 10 squared 3x dx. 10 squared 3x. Now, first of all, I don't really like it. It's not that I don't like it. It just makes it more obvious if you write it as a power just outside of bracket. So you can write this as tan 3x all squared. Now, from this kind of looks like we have something like this going on. D dx of something squared, right? That's a clear power rule over here. It's in the exact same form as this. So that's my most outer function because it fits that form, right? Um, and then this means my inner equation is going to be tan 3x. Okay. Now, tan 3x doesn't exactly fit this equation either. Why? Because there's not just an x here, there's 3x, right? And I get it. This is 3x is fairly simple, but this could extend to things that are more complicated. Uh, I could I could make it more complicated actually. Hold on. Let me just start this question all over again. So I'll keep the squared there. I'll make this thing x cubed, x cubed, x cubed. Okay, so the first step is still the same. Again, it doesn't really matter what goes on the inside. You have to kind of break it down from the outside. So you have to figure out what the most outer function is, and then what's one step inside that, and then what's one step inside that, to the point where you can kind of just it just kind of all goes away, right? So the most outer is something like that, which is the power rule. You do that first, and then I'll chuck this over here because that's like the next layer. Um, the next layer we have the tan x cubed left over, but this obviously takes the form of tan of something, right? Takes the form of this thing, or rather, I'm just gonna replace all the x's like just with a box, and the box can just represent whatever can go in there, right? Okay, so that's the next in a step, and then what's next is I still have the x cubed left, right? And this obviously just follows the power rule again. So yeah, those are the three functions that there are for this question, I guess. So this is the most outer. You do that first, and then you do the tan, and then you do the cube. Um, yeah, yeah. So in practice, it would look something like this. So how do you differentiate this? You do two of whatever's on the inside. Again, let me stress this. You don't touch this. You deal with one function at a time. So you deal with this at a time. Like you deal with this. You don't touch anything on the inside. Um, and then you deal with this. You don't touch anything on the inside. And then you deal with this. And then you're done. So I'm still dealing with the first function, and then it's gonna have tan x cubed on the inside, and then the next layer I'm gonna have the derivative of tan, right? Which is sec squared of whatever's on the inside, and I'll have to find the derivative of the next thing, which is 3. I think that was an x, right? Yeah, 3x squared, and I'm done basically. Um, I'm hoping I'm not overcomplicating these sort of things for you. But with this, if you wanted to use the right method, because I'm technically sticking to the left one where I'm just kind of trying to observe what's what. If you use the right one where you're trying to form this kind of chain rule, it would work as well. And the way you make sure it works is that whatever you cancel out, just make sure you get the idx at the end. So technically speaking, if I introduce two different variables instead of just u, like dy dx equals to dy du times du dk times dk dx, that's three nested equations basically, but it would still work for whatever question we're looking at. And I could do that actually. So over here, let's just say my most inner function, let's just call it k, is equal to x cubed. So my y would be equal to tan squared k. So it looks a lot simpler already. And then the next inner function was tan, right? Like that, 10k. So my y is actually u squared. And I'll put this here. Oops. So dy du is equal to 2u squared. Du dk is equal to sec squared k. And then dk dx is equal to 3x squared. Um, and the answer is going to be 2u squared times sec squared k times 3x squared. And of course, you have to make the substitutions again, right? Like subbing this back in here, something like you know what to do. And you can see how they have the same structure. That's how I think about this sort of thing. So I'm hoping I'm not overcomplicating these things for you. And yeah, I'm gonna stop the recording here.